Honeybees are fascinating creatures for a number of reasons. Their incredible work ethic, the sugary sweet syrup they produce, and their intricate social structure. But another reason is that honeybees are, in fact, excellent mathematicians. Scientists claim that tiny insects can calculate angles and can even comprehend the roundness of the Earth. But there's particular mathematical bee genius behind the most important aspect of honeybee life, the hive. Just like humans, bees need food and shelter to stay alive. The hive is not only the bees' home, but doubles as a place to store their honey. Since it's so central to survival, honeybees have to perfect the hive's architectural design. If you examine any piece of honeycomb, you'll see that it's constructed from tightly packed hexagonal or six-sided cells. Of all the possible designs, why do honeybees choose this one? To understand, you need to think like a bee. Bees need a secure place for their entire colony to live. Similarly, there needs to be a place where their nectar can be stored and ripened suitably, until it turns into honey. That means there's a need for some serious space efficiency. A good solution is to build little storage units or cells just big enough for a bee to fit into, which can also double as the containers in which nectar is stored, the bee's very own honey jars. The next thing is to decide what the little cells should be made out of. Bees don't have beaks or arms to pick up things, but they are capable of producing wax. The thing is, producing it is a lot of hard work. Bees have to consume 8 ounces of honey to produce just 1 ounce of wax, so they don't want to waste it. So they need a design that allows them to store the largest possible amount of honey using the least amount of wax. What shape does that? Imagining for a minute that all bees had to attend Architecture Academy and go to math class. Let's say they asked their geometry teacher, what shape would give us the most space to store our honey but require the least amount of wax? And the geometry teacher replied, the shape that you're seeking is the circle, leaving the bees to return to their trial construction site and begin building their honeycomb using circular cells. After a while, some of them might have noticed a problem with their design. Small gaps between the cells. We can't even fit in there. That's wasted space, they might have thought. So, ignoring the geometry lesson and taking matters into their own hands, the bees went back to the drawing board to rethink their beehive design. One suggested triangles. We can use triangles, look, they fit together perfectly. Another bee suggested squares. Finally, a third bee piped up and said, pentagons don't seem to work, but hexagons do. We want the one that will use the least amount of wax and be able to store the most amount of honey. Yes, I think that's the hexagon. Why? It looks more like the circle than the others. But how do we know for sure? To find out, the industrious insect architects calculated the areas of the triangle, the square, and the hexagon and found that the hexagon was, in fact, the shape that gave them the most storage space. They agreed on an ideal size and returned to work. The space-efficient comb that is a bee's trademark today is probably the result of this trial and error, but over long periods of evolutionary history. However, it paid off. Peek into any hive, with your protective goggles and netting on, of course, and you'll see the end result, a beautiful, compact honeycomb that any architect would have been proud to design.
At first glance, a fire ant hill, or mound as it's properly called, looks impossibly small. And yet, a colony of up to 250,000 ants call it home. But here's the secret. That mound is just the tip of an enormous iceberg. So let's take a closer look at what's inside an anthill. The mound is really the top of an enormous underground structure, the nest, which is basically a giant nursery, a nice, cozy place to raise babies. A lot of babies. Their mother, the queen, roams around the nest while laying 1,500 eggs a day. Now, all those baby ants need to live in a narrow temperature range to grow. So that nest sports temperature-controlled rooms, and it does so without the help of an AC unit. The secret is in the design. The nest is arranged like an ice cream cone. At the top, you have the mound, the ice cream, as it were. Because it's above the surface, it warms from the heat of the sun. So the babies can snuggle up in toasty chambers networked throughout the mound. But they can't stay there all day, or they'd get too hot. That's where the cone part of the ice cream cone comes in. The mound is connected to several vertical shafts that plunge up to 2 meters beneath the ground. That's taller than most humans. Throughout the day, adult ants ferry the babies up and down the shafts, chasing that perfect temperature for their young charges. The nest also sports dozens of tapering tunnels that branch off from these main shafts. These connect to small chambers where the ants rest, eat, and feed the babies until it's time to move the little ones once again. Now, there's one more type of tunnel inside the nest, but only a few ants ever use it. You see, someone needs to find food for the rest of the colony, but running around outside the nest is dangerous business. That's where forager tunnels come in. These are a couple of horizontal passages buried just a few centimeters from the surface. But they run throughout the entire territory, which can cover up to 185 square meters of land. By scurrying through these passageways, the scouts can stay underground as long as possible. But unfortunately, the nest and all its roads can't protect the ants from every threat. It turns out all sorts of critters sneak inside fire ant nests. And while many of them are actually harmless, others are horrible house guests. For example, beetles burrow into the nest and devour the eggs and larvae. But invaders aren't the only threat to the colony. Occasionally, clueless humans or major floods disturb the nest. And when that happens, the fire ants have only one option: leave. Once a year, on average, the colony will move out and build an entirely new nest from scratch. And best of all, they only need a few days to do it. That's right. Practically overnight, meters upon meters of tunnels can pop up in your yard. And all you'll notice is a tiny mound.
Emperor penguins are one of nature's great survivors. They can endure the extreme cold of an Antarctic winter, where temperatures can plummet to minus 40 degrees Celsius. One by one, the male emperor penguins lock themselves together in a tightly packed group to keep warm and shelter from the intense winds. These huddles can contain as many as 4,000 penguins. And they are constantly moving. Those on the outside push forwards to get closer to the warmth in the center of the group and away from the full force of the Antarctic storms. But the penguins on the inside of the huddle also move around to stop themselves from getting too warm. Recent studies have shown that temperatures at the center can reach an incredible 37 degrees Celsius. So the penguins move away to avoid overheating, with others replacing them.
So what's the science behind huddling? Exactly how does it work? Well, we have a thermal imaging camera trained on me to help explain exactly what's going on. Now, heat is a thermal energy that's constantly flowing around us. And as it flows, it naturally moves from hotter objects to colder objects. To show you what I mean, I'm going to fill this solitary mug in the snow with some hot chocolate. Now you can see it's hot, white or yellow in the center, but very quickly it's losing that heat to the colder air around it. But if I fill all of these mugs of chocolate huddled together, you should be able to see something very different is happening. All of the mugs are losing their heat much less quickly, particularly the one in the center. And that's because it's protected by the hot mugs around it, but also it's gaining some heat from the collective huddle that's hotter than it is. Therefore, the heat is transferring to that mug in the center. In just a few minutes, you can clearly see the difference, can't you? This cup is now completely cold, having lost all its heat to the elements, while this one is nice and cozy and warm in the center.
Because an octopus has almost no hard parts at all, except its beak, it can squeeze through any hole as long as it's larger than its eyeball. This allows the octopus to hide in very small crevices, a certain evolutionary advantage when escaping large predators like sharks or dolphins. But the soft-bodied octopus evolved an even more clever way of evading detection. They are masters of disguise. Watching this clip of an octopus, you can see just how quickly and drastically it can change colors. In slow-motion reverse, you see the color change spread across its body. The 3D texture of the skin also changes to match the surrounding seaweed and coral. In the blink of an eye, it has almost completely blended in with its surroundings. Cephalopod camouflage is among the most dynamic in the animal kingdom and relies on a system of extremely sophisticated tissues. Chromatophores are organs that are speckled across the skin of the octopus, like freckles. They contain tiny pigment-filled sacs, like little balloons full of different colored dye, which can be black, red, or yellow. The pigment sacs are surrounded by radial muscles, which can stretch the sac to reveal the pigment's color. Just like balloons full of dye, when stretched, their pigment color appears bright and vibrant. Depending on which sets of sacs an octopus opens or closes, it can produce patterns such as bands, stripes, or spots, helping to turn itself into a rock, a coral, or a kelp in an instant. But if the octopus needs to produce colors outside of black, red, and yellow, it uses another layer of reflective structures in their skin called iridophores. They are stacks of very thin cells that lay beneath the chromatophores. They contain a protein called reflectin that bounces certain wavelengths of light back out. They are responsible for the metallic blues and greens that appear to shimmer on the skin of the octopus. Beneath that layer is yet another layer of reflective tissue called lucifores. These reflect ambient light, usually producing white hues. By combining reflection from the iridophores and lucifores with the correct patterning of the chromatophores, the octopus can create a very convincing copy of its surroundings. But the octopus has one more trick up its sleeve, allowing it to disappear in plain sight almost completely. Using a structure called papillae, it can change the texture of its skin, creating ridges and bumps that rise and fall. This helps the octopus match its surroundings even better. With all these tools, the shell-free, soft-bodied octopus has been able to deceive an ocean full of predators for millions of years.
Here's a riddle for you. A man is standing in the desert. He's thirsty, parched, and surrounded by fresh water. But he can't drink. Why? He's surrounded by fog. This isn't actually a riddle. It's a real problem scientists have been trying to solve for years. And the solution might just be this little beetle. It might not look like much, but it can pull water out of thin air.
By 2025, nearly a quarter of us could be living in places where water is scarce. Now, scientists trying to tackle the problem have turned to a tiny beetle for help. The fog-stand beetle is native to Africa's Namib Desert, one of the most arid areas of the world. But what it lacks in rainfall, it makes up for in coastal fog. And it's this the beetle depends on for survival. It basks in the fog, standing upside down on top of sand dunes. Its back is covered in bumps that have water-loving tips and water-repelling slopes. This structure encourages tiny droplets of fog to stick to the surface. As the droplets coalesce to form larger drops, gravity causes them to roll down its back and into its mouth. Everybody needs water to live, and this clever beetle will continue to teach us innovative ways to make the most of it.
While delivering messages on horseback or on foot was satisfactory, it also came with a lot of unpredictable variables, including dishonest messengers, accidents, loss of messages, unexpected delays, and a lack of guaranteed privacy. Therefore, not only was a faster delivery system desired, but also a more reliable one. Honestly, how fast can this tiny horse really run? What if the message is urgent? Messenger pigeons. More than 3,000 years ago, the first such improvement on message delivery was made when homing pigeons were first introduced. While studying the patterns and movements of birds, it appeared that they had a wonderful sense of direction and could consistently find their way back to their nest. Even after foraging, hunting, and soaring for miles in every direction, they were able to guide themselves and, strangely enough, find their way home. Pigeons tend to be easy to capture, quick to breed, relatively docile, and highly in tune with their sense of direction. In particular, rock pigeons were chosen and interbred to create homing pigeons, essentially birds that could find their way home. These pigeons would be trained very carefully, gradually being taken further and further from its nest before being released and flying home. In this way, pigeons could be programmed, for lack of a better word, to fly from a range of different locations. Pigeons could use visual cues like natural landmarks and gradually developed a known path back to its home base. Unfortunately, this meant manually transporting large amounts of pigeons in one direction before having them released with a message attached to their leg, hoping that they would return to the original location. These messages were typically small rolls of parchment or paper, stored in a small glass or metal tube. Once the message was written and stored, the homing pigeon would be released to fly home, thus delivering the message and skipping over traffic, natural disasters, dishonesty, bad network, and human error. Now, rock pigeons were particularly gifted in this homing ability due to their strong magnetoreception skills. For those of you who don't know, magnetoreception is an innate ability in certain life forms to detect and orient themselves based on magnetic fields. Humans lack this ability, but many bird species have the skill in varying degrees. Rock pigeons that showed the strongest ability were bred to create powerful and reliable homing pigeons. Interestingly enough, it has been found that homing pigeons are much more accurate going long distances in the north and south direction rather than east and west, due to the natural direction of the magnetic fields flowing between the North Pole and South Pole. The biggest trouble, obviously, was the one-way trip for the birds over land before they could be released to fly home. Fortunately, this issue was solved through experimentation. It was found that homing pigeons could be fed in one place and deliver messages to the other. In this way, the birds could be coaxed to fly back and forth between 2 points, carrying messages to and from. The speed, efficiency, and lack of human variability was finally achieved. While seeing homing pigeons in the modern world would be something of an oddity, there are still those who train and race pigeons over great distances, so the tradition definitely lives on. In the past, however, homing pigeons were essential aspects of politics, diplomacy, and even military action. Yes, homing pigeons were used to share messages during wartime, as they were able to get through enemy lines much easier than a man on a horse. This earned them the name war pigeons, and in some fashion, they were used up until World War II. Historically, however, Genghis Khan used the pigeon post to stay in contact with distant points of his empire, And even in ancient Greece, homing pigeons were used to announce major events, like the Olympics. In the 12th century, a rather extensive network of homing pigeons between Syria and Baghdad was established to link the two. One of the final pigeon posts in active duty was in India, but the pigeons were officially retired in 2002. Yes, while the training methods and means of communication differed in various parts of the world, the recognition of birds as reliable messengers occurred throughout history.
When desert locusts are well fed, they're solitary creatures. But when food becomes scarce, hungry, desperate locusts crowd onto small patches of land where they can still find something to eat. Contact between different locusts' hind legs sets off a slew of reactions that change their appearance and behavior. Now, instead of shunning their peers, they seek each other out. The locusts eventually start marching and then fly away in large numbers seeking a better habitat. These gigantic swarms can host millions of insects and travel thousands of miles, devastating vegetation and crops. They stay close to each other, but not too close, or they might get eaten by their hungry neighbors. When many individual organisms, like locusts, bacteria, anchovies, or bats, come together and move as one coordinated entity, that's a swarm. From a handful of birds to billions of insects, swarms can be almost any size. But what they have in common is that there's no leader. Members of the swarm interact only with their nearest neighbors or through indirect cues. Each individual follows simple rules. Travel in the same direction as those around you, stay close, and avoid collisions. There are many benefits to traveling in a group like this. Small prey may fool predators by assembling into a swarm that looks like a much bigger organism. And congregating in a large group reduces the chance that any single individual will be captured. Moving in the same direction as your neighbors saves energy by sharing the effort of fighting wind or water resistance. It may even be easier to find a mate in a swarm. Swarming can also allow groups of animals to accomplish tasks they couldn't do individually. When hundreds or millions of organisms follow the same simple rules, sophisticated behavior called swarm intelligence may arise. A single ant can't do much on its own, but an ant colony can solve complex problems, like building a nest and finding the shortest path to a food source. But is there anything we can learn from collective swarm-based organization? When it comes to technology, the answer is definitely yes. Bats can teach drones how to navigate confined spaces without colliding. Fish can help design software for safer driving. And insects are inspiring robot teams that can assist search and rescue missions.
Cities form a completely new habitat that we have created, and we clothe it in brick and concrete and glass and steel, which are impervious surfaces that plants can only root in with the greatest difficulty. Also in cities we find the greatest concentrations of chemical pollution, of artificial light and noise. And we find wild mixtures of plants and animals from all over the world that live in the city because they've escaped from the gardening and aquarium and pet trade. And what does a species do when it lives in a completely changed environment? Well, many, of course, go sadly extinct. But the ones that don't go extinct, they adapt in spectacular ways. Biologists these days are beginning to realize that cities are today's pressure cookers of evolution. These are places where wild animals and plants are evolving under our eyes very rapidly to suit these new urban conditions, exactly like the ant beetle did millions of years ago when it moved inside an ant colony. We now find animals and plants that have moved inside the human colony and are adapting to our cities. And in doing so, we're also beginning to realize that evolution can actually proceed very fast. It does not always take the long lapse of ages. It can happen under our very eyes. This, for example, is the white-footed mouse. This is a native mammal from the area around New York, And more than 400 years ago, before the city was built, this mouse lived everywhere. But these days, they are stuck in little islands of green, the city's park, surrounded by a sea of tarmac and traffic. A bit like a modern-day version of Darwin's finches on the Galapagos. And like Darwin's finches, the mice in each separate park have started evolving, have started to become different from each other. And this is my colleague Jason Munshi-South from Fordham University, who is studying this process. He is studying the DNA of the mice, the white-footed mice, in New York City's parks, and trying to understand how they are beginning to evolve in that archipelago of islets. And he's using a kind of DNA fingerprinting, and he says, if somebody gives me a mouse, doesn't tell me where it's from, just by looking at its DNA, I can tell exactly from which park it comes. That's how different they have become. And Jason has also discovered that those changes, these evolutionary changes, are not random. They mean something. For example, in Central Park, we find that the mice have evolved genes that allow them to deal with very fatty food, human food. 25 million people visit Central Park each year. It's the most heavily visited park in North America. And those people leave behind snack food and peanuts and junk food, and the mice have started feeding on that. And it's a completely different diet than what they're used to. And over the years, they have evolved to suit this very fatty, very human diet. And this is another city slicker animal. This is the European garden snail. Very common snail. It comes in all kinds of color variations, ranging from pale yellow to dark brown. And those colors are completely determined by the snail's DNA. And those colors also determine the heat management of the snail that lives inside that shell. For example, a snail that sits in the sunlight, in the bright sun, if it has a pale yellow shell, it doesn't heat up as much as a snail that sits inside a dark brown shell. Just like when you're sitting in a white car, you stay cooler than when you're sitting inside a black car. In the center of the urban heat island, we find that the snails have evolved more yellow, more lighter colored shells. Now, the city snail and the Manhattan mouse are just two examples of a growing list of animals and plants that have evolved to suit this new habitat, this city habitat that we have created. And in a book that I've written about this subject, the subject of urban evolution, I give many more examples. For example, weeds that have evolved seeds that are better at germinating on the pavement. Grasshoppers that have evolved a song that has a higher pitch when they live close to noisy traffic. Mosquitoes that have evolved to feed on the blood of human commuters inside metro stations. And even the common city pigeon that has evolved ways to detox themselves from heavy metal pollution by putting it in their feathers. Biologists like myself all over the world are becoming interested in this fascinating process of urban evolution. We are realizing that we're really at a unique event in the history of life on Earth, a completely new ecosystem that is evolving and adapting to a habitat that we have created.